Hi, everybody. Thank you for coming. My name is Rahul Pathak. I'm the Senior Product Manager for Amazon Redshift. Appreciate your time. Today, you'll learn a little bit about why we built Redshift, how we achieved some of the performance that we talk about, and ease of use. And then you'll also hear from one of our early customers, Airbnb. We've got Henry and Flo here to talk about their experiences with Redshift and how it fit into their infrastructure. So Redshift exists because our customers asked for us to build them a way to do data warehousing that didn't require tons of upfront investment, that made it easy for them to provision data warehouses. And we also wanted to deliver something that was fast, cheap, and easy to use. And finally, we wanted it to be compatible with the tool sets that people use today. And that means SQL and JDBC and ODBC. So I'll talk about all of those in just a second. And what we set out to build was a fast, petabyte-scale data warehouse service. And our goals were really to build something that was 10 times faster than traditional databases for analytic queries, and at least a tenth the cost of traditional data warehousing solutions. And we also wanted it to be really easy to use. And we're off to a good start. We're excited about the response that we've seen in the market. I think you heard Andy at the keynote talk about Redshift being the fastest growing AWS service. And while we're excited about our beginning, we also know we have a ton of work to do in terms of improvements we'd like to make. And as always, I think we'd like to make things faster and easier to use and improve along all the dimensions that matter to our customers. And so let's talk about performance. So at data warehousing at scale, I/O really becomes one of the important factors. And what we're trying to do with Redshift is use columnar technology to reduce the amount of I/O that we need to do. So if you look at this table in a traditional row-based store, if you're trying to get the average of the amounts, you're going to have to read every single item in your table, do the full scan, and then throw away 3/4 of the data just to get the column that you care about. So you end up doing more I/O than you need. Whereas with a column-based system, columnar data stored sequentially on disk, you can go to the start of the column that you want, and then you'll get just the read that you're looking for. And you end up doing only the I/O that you want. You just read the data that you need to answer the queries that you're working on. The other benefit with columnar technology is you get compression benefits. So with like data stored, sorry about the advancing here, with like data stored on disk sequentially, you're able to take advantage of the fact that there's similar data next to each other and get compression. As you can see, we use multiple different types of compression algorithms based on the data sets that are being loaded. And Redshift is smart enough to analyze and sample your data when you first load an empty table and to pick the compression scheme that's most suited for that data. So in real-world data sets, our customers see anywhere from 4x to 8x savings over their entire database. And so what that means is a 4 terabyte database coming from a traditional data source becomes a 1 terabyte data warehouse in Redshift. And that's real-world data. Some columns, you can imagine if you had a column just containing gender with 2 values, that would compress far better. And so this is just taken as a whole over their data set. And the big benefit for customers with this is, one, it costs less, so more of your data will fit into a given size Redshift instance. And the second thing is when we do end up doing reads, we get more data back from the system. So we're more efficient. It leads to better performance. Another technique for performance and I/O efficiency that we use in Redshift extensively is zone maps. And the idea here is to keep track of the min and max values in every block that's on disk. And so when you have sorted columns, zone maps allow you to essentially focus on the data that you need. So if we know that a data isn't in a given block to answer the query that we're trying to run, we can skip over it. And this is why sort keys come into play, and we'll talk about data distribution on the system in a little bit, but it allows you to focus on I/O that you need to do. And then when we decide that we have to do I/O and actually need to go to disk to do reads, we want them to be as high performance as possible. And so we use direct attached storage, and I'll talk about our instance types, but they're optimized for high performance I/O. And because we maximize the amount of performance you get, because the drives and the CPU and the memory systems are all local, we also have to manage durability in an EC2 environment, and we take care of that for you as well. So you get the benefits of performance, and then as a managed service, we take care of management. And then with large block sizes and with compression, when we do end up doing a read, we get as much relevant data as possible. So overall, a lot of effort's been put in to try and figure out how to get the most performance out of the system. So from an architecture perspective, Redshift is designed to be run as a clustered data warehouse, although we do have a single node variant available that gives you a low-cost, easy entry point. As you can see, you've got JDBC and ODBC to connect your SQL clients. We use the Postgres wire protocol. You can download drivers from the Postgres website, so really any system that speaks Postgres over JDBC or ODBC you can use to talk to Redshift. There's a leader node, which is your SQL endpoint. That stores system metadata, and it also coordinates query execution. And then the compute nodes is where all the data is stored. So those systems have the drives, and there's a CPU and RAM that operates on your queries. And those are loaded and backed up in parallel. We'll go into each of those operations as well. And the whole idea here is you issue queries at the leader node. Those are then distributed and executed in parallel across the cluster, maximizing the resource utilization to try and get you back results as quickly as possible. So our hardware platform is one that's optimized for data processing. It's actually it's also available on EC2. It's the high storage instance. It was announced at reInvent in November, and it's a pretty beefy box. It's got 128 gigs of RAM, 16 cores, 24 spinning disks on it, 24 spindles for parallel I/O, and 16 terabytes of compressed user storage. And so at 4x compression, you can imagine a 64 terabyte database will fit onto one of these nodes. And you get over 2 gigabytes per second scan rate between the drives and the CPU system. So that's our 8 extra large. That's also available on EC2 if you want to run your own systems there. And in Redshift, uniquely, we make it available in a 1/8 size, which is the single XL. And that's 1/8 on all dimensions. So 16 gigs of RAM, 2 cores, and 2 terabytes of storage. Again, this is optimized for high performance on data processing. It lives in our HPC, which is our high performance computing network, so non-blocking, non-oversubscribed network in that system. And it's really the underpinning of Redshift from a hardware perspective, so the other part of performance. So another aim with performance is Redshift is a clustered system, so we try and do as much work in parallel as we can. And so this is a look at what happens in the leader node when you issue a query. We actually will parse your SQL, do any logical optimizations that we can, and then we'll take advantage of the system's knowledge of how data is laid out and the statistics on the tables that you have to build a query plan. That then goes to an execution engine where we actually generate and compile C++ code and then push it out and execute it on each of the compute nodes in parallel. And that compiled code is actually stored in the system and reused. So even though parameters change, we don't have to incur the compilation penalty more than once. And there are multiple threads on the compute nodes executing this compiled code in parallel. Again, a key part of how we're trying to get performance. We want to divide and conquer the workloads. And as you've seen in the architecture, it's a scale-out system, so you can add more nodes, both to get storage, but also to get performance, because you'll get more memory, more CPU cores acting on a smaller amount of data if your data size is fixed and your node size goes up. And in addition to querying, we've also focused on making data loads parallel. And the reason is we don't want you to have to spend extra time loading a cluster when you have 2 nodes or 20 nodes. And so data loading at the moment can be done via a single SQL copy command. It points to an S3 bucket or a DynamoDB table. And it then loads each compute node in parallel simultaneously. And on the compute nodes, for each core, we have a process called a slice. And so on a single XL node, you have 2 slices. And on the 8XL, you have 16. And you should map the number of input files that you're loading to the number of slices, because each of those slices is loading data in parallel. The nodes are also all connected via 10 gig E. And so if data needs to be redistributed from one node to another, that'll happen automatically. One part of columnar systems is that whenever you have data that needs to be joined, you want to have it live on the same node as much as possible, because joins that are local to the node will perform better than joins that have to go over the network. And so one of the options that you have when creating tables is a choice of a distribution key. And this is how you physically lay out data. And so if you can think about it, for example, if you have a customer ID and a customer sees ads and a customer also has accounts and makes transactions, you might want to distribute on customer ID so all data for that customer lives on the same node. And therefore, when you run joins for that customer, all this data is node local, and you'll get better performance out of the system overall. The other thing that happens here is that this is all done behind the scenes, so all you have to do is pick the number of nodes, define your table, and then load your data. You can also do SQL loads using inserts and updates via JDBC and ODBC. That does not perform as well as the parallel loading mechanism, so really it's a question of looking at your data velocity and figuring out which mechanism is best. We do recommend the S3 or the DynamoDB pathway, and we'll be adding more of those over time. With DynamoDB, you use a copy command as well. You specify a table, and you can tell it how much of your provision throughput you want to use, and it will then load that data into Redshift in parallel again. We also have invested a lot of effort in continuous backup and easy restores, and so backups are also done at the node level. They're done in parallel. They are automatic, and they are incremental. And so anytime data changes in a cluster, we will kick off a backup process that will asynchronously copy data to S3 and just copy what's needed. So if your data doesn't change, you won't see any new blocks in S3. And that system snapshot period is configurable. So it defaults to 1 day. You can set it to up to 35 days, and we'll just age out old data as that window slides. The other thing that you can do is take a user snapshot at any point in time. So say, for example, you've just loaded data and you want to freeze cluster state. You can trigger a snapshot via the console or an API call, and that will give you the state of that cluster. That'll be retained until you explicitly delete it. So you have a lot of control over how your cluster's backups are stored. And at any point, you can restore a new cluster from any of those snapshots, and we will set it up, reload the data onto it, and make it available to you for querying. One feature that we spend a lot of time on to try and minimize the time it takes for your cluster to start performing normally when we restore it is a feature we call streaming restore. So if you think about it, we have nodes that can store up to 16 terabytes of data on each one, and you don't want to have to wait for 16T to be loaded on each node when you do a restore. And so with streaming restore, as soon as the node is available and connected to your cluster, which takes minutes, we begin bringing back data that was most recently used first and allowing you to execute queries. And then the system will page in data from S3 as needed. And what we found for customers is that because they typically have some time locality or access patterns in their data, once just 3 to 5% of the data is back, query performance is normal for most queries that they would run. Again, all automatic, done behind the scenes. So resize is another operation that's really easy to do in the cloud. You can pick the number of nodes in your cluster. We let you start with 1, scale up to 100 of the larger ones. We'll talk about the details of that in a second. And the resize operation, what we actually do is provision a brand new cluster in the background, and we do a parallel node-to-node copy. From each node, we'll move data from your source cluster to your target cluster. And your original cluster is available for reads while this is happening. And if you think about it, what this means is the time it takes to resize is really limited by the amount of data per node on the smaller cluster. So if you have 3 nodes with 4 terabytes each on them, a 12T system, and you're moving the same amount of data to a 4-node system, you'll have 4 terabytes per node on the source cluster, and that'll be the rate-limiting step of the resize operation. And naturally, we only charge you for your source cluster until your target is active and your SQL endpoint's been cut over. And once the resize is complete, we'll automatically use DNS to switch your SQL endpoint over to the new cluster, so you won't have to do any application configuration changes. So from a scalability perspective, what we tried to do with Redshift was to make it very easy to really scale up as your needs required. And so you can start with a single Excel node that has 2 terabytes of customer available compressed storage on it. And those can be run in a clustered model, up to 32 of those at a time, and that gets you 64 terabytes of storage. At any point, you can switch over to the 8XL size. That requires a cluster, a minimum size of 2 nodes, so that's 32T. And you can chain 100 of those together to get to 1.6 petabytes. We've already started hearing requests for that limit to be raised from some customers, so we will look at that. And the there's really no difference between running 8 single X cells or 1 8X cell. It really comes down to your scaling increment. They're exactly 1/8 of the larger systems on each size. And along with ease of provisioning and scalability, one of our goals with Redshift was to make it really easy and cost-effective to analyze all of your data. So what we're seeing is customers who throw away a ton of their data, either to fit in to size limits of cheaper editions of software that they already have, or because their existing systems just can't handle the scale. And what we wanted to do with Redshift was to make it economical to analyze much more of your data so you can focus on really what are the right questions, what data do I need to answer it, and not how much is it going to cost me to analyze this. And in keeping with our general pricing philosophy at AWS, you can pay by the hour on demand. So the single node pricing that you're seeing here, which is 1/8 the pricing of the 8XL, is 85 cents an hour for a single 2 terabyte node. And that works out to an annual cost of about $3,700 per terabyte per year. And then we have our reservation models. And this is where you can prepay a slightly larger upfront payment in return for lower ongoing fees and to give us some visibility into capacity needs. And in return, with a 1-year reservation, you get a 40% discount. And then with a 3-year reservation, you get a 73% discount, which comes down to under $1,000 per terabyte per year. And that's traditional data warehousing systems are at the 20K per terabyte per year range and higher. So this is a significant change in the pricing model, and we're seeing some of that translate into A, adoption, but also B, customers finding a lot more use cases for data warehousing than they did before. The other part of this is we don't charge you for the leader node. That's something that we absorb, and pricing model is very simple. You can scale up, scale down. It's the number of nodes that are running per hour that determines your costs. So we talked about performance and price. Now, ease of use was another thing that we wanted to spend a lot of time on. Traditionally, data warehousing requires lots of DBAs. It requires complex node setup. You have to understand the networking of the system. You have to deal with backups. And all of those things just take time and prevent you from focusing on your application and your data and the insights you want to drive from that. And so what we've done with Redshift is we've designed a system that is easy to use, easy to provision, and we've also tried to simplify day-to-day operations like security, backups, resizing. And provisioning is a 15-minute operation, and we're always working to make that faster, although last week in a customer meeting, they started laughing when I told them that it was 15 minutes because they were used to looking at weeks from a traditional data warehousing model. And all you have to do is choose the size of nodes and the number of nodes you want in your system. We support VPC out of the gate, so you can make those selections and you can launch it. And as with all of our services at AWS, there are also APIs and command line tools to enable you to do this. And you have full control over your resources with things like identity and access management. You can decide which users can create clusters, provision clusters, do any of those things. So it's fully programmable from that perspective. Now, the common thing that people want to do is look at query performance. And so we spent a lot of effort investing in our console to provide you with information on queries when they're running, to give you a sense for what resources they consumed. So what you're looking at here is a time chart. The horizontal bars are queries that ran on the system. You can hover over them, and then it'll shade the resource utilization on the nodes in the cluster as when that query was being run. You can see what we're looking at here, that green one at the bottom left, and it's shaded on the nodes. The 2 compute nodes in this system have pretty even distribution of data, which is what you want to see. You don't want to see any hotspotting on a particular node. You'll notice utilization is pretty similar. And you'll see the leader node is doing close to nothing because it's just coordinating. So this is data that's well distributed. You'd want to see this sort of pattern when you're executing queries. The other thing that you get is you get the SQL for the query on the right-hand side. And if you click on the query, you can actually get the explain plan. So you know exactly what the system did and can troubleshoot from there. And all this data is also available to you through access to system tables directly from SQL, from your SQL client of choice. Resize, we've talked about the mechanics of it. It's a very simple operation with Redshift. All you're doing is picking the number of nodes and the type of nodes and then clicking the button. Also available via API. Security is also built in, so we spend a lot of time making sure that Redshift had really was able to take advantage of everything that we offered at AWS from a security perspective at launch. And so we have SSL to secure data that's in transit. You'll enable this on the client side and then can connect to ensure that all data flows are encrypted. We also use SSL for any data that we move to and from S3, so there's encrypted data connections between S3, DynamoDB, and Redshift as well. SSL is an option that you can enable on your end, and it's a choice that you can do at any time. We also have encryption of data at rest. So this is hardware-accelerated AES 256. We do this at a very low level in the subsystem, so every block that's ever written to disk, whether it's data that you've stored when you loaded it, but also temporary data that spills over, everything is encrypted. And then because we're continuously backing up at a block level, every block that's put into S3 is also encrypted when you enable this option. And we actually use a multi-layer key mechanism where each block gets its unique key that's generated. We use that to encrypt each block individually. There's then a cluster key which encrypts all of those keys, and yet another key which encrypts that, and that's stored in an encrypted fashion off cluster. So multiple layers on that front. We'll continue to innovate on that side. And that's an option that you can enable at any point, either at cluster creation time or by modifying your cluster. It does have a performance impact where in our testing we see about 10 to 15%, and that's why it's not enabled by default. It's really up to our customers to make the decision of what they'd like to use. Each Redshift instance is provisioned solely for the customer that created it. All of those compute nodes exist inside their own private VPC. Our VPC is the Amazon Virtual Private Cloud, so it lets you logically isolate a section of the AWS cloud and set up your own networking rules and access rules. And when we provision Redshift clusters, we actually put the compute nodes and the leader node into their own private VPC, so nothing can access the compute nodes directly. Even data loading operations are pull operations, so we actually pull data in. Nothing's pushed onto them. And you can also set up your own VPC and so run Redshift inside of that and really lock down the system as much as you'd like to and design it for your architecture and infrastructure. So the other part of operations is really taking care of your data. And we use local attached storage, as I mentioned, for performance. But on EC2, local storage is ephemeral. And when you're dealing with multiple terabytes of data per node, you don't want ephemeral is not a good thing. So we've spent a lot of time investing on durability to make sure that you don't need to worry about the durability of your data. We'll take care of that for you. And that's generally a theme with all of our managed services at AWS. So anytime you load data into a cluster, we will synchronously replicate it onto other drives within that cluster. And so if a write is successful, multiple copies of that data exist within the cluster. What this allows us to do is to tolerate drive failures transparently. And if you think about it, if you're running a 100-node system with 24 drives per node, that's 2,400 spindles going all at once. And so just given probabilities, you're bound to see drive failures at some point in time. And we wanted the system to be able to handle those gracefully. So you have multiple copies in the cluster itself on different nodes to minimize the blast radius. We then back up to S3 continuously, automatically, incrementally. And S3 is a highly durable system designed for 11 nines of durability. And so with all of these multiple copies, we'll make sure that your data is available when you need it. And we're continuously monitoring everything. So every node is continuously monitored, all components of the system. We will recover, reboot, replace nodes as needed to make sure that your cluster is available. And the streaming restore applies even in the case of a single node. So if a node needs to be replaced, as soon as we can connect it back up, you'll be able to resume querying and go from there. Another important point to mention here is that we use S3 for both data loading and for snapshots. S3 is a regional service. So with AWS, within a given region, we have what we call availability zones, which are multiple isolated data centers with their own power, networking, cooling. And with S3, you can restore your snapshots into any other AZ or availability zone within a given region. So that gives you options in case there is an outage of some kind or an event. You can bring up a new cluster using exactly the same data that you had before in a different zone. So we've really designed Redshift to be a central data warehouse to be used with as a central place to analyze really all of the data that's generated within an organization. And we see customers who use traditional OLTP stores. They have RDS. Maybe they're running their own databases either on EC2 or on-premise. We have customers running NoSQL data stores on EC2 or using DynamoDB for real-time data capture. We also see MapReduce and EMR used in conjunction with Redshift a lot. It's great for processing unstructured data, turning it into columnar delimited data that can then be easily imported into Redshift. And so because Redshift exists really as a hub for a lot of these data flows, we've designed it to talk to multiple data systems. There's that single SQL integration with DynamoDB and S3. And through partners and tools and really data movement on S3, you can bring data in from any other system as well. We provide multiple options for loading data. And so we have numerous partners and ways to upload data in parallel to S3. S3 can really help you, if you're running multiple uploads, saturate your outbound pipes, so it'll take data as fast as you can throw at it. We have AWS Import Export, which is when you essentially ship us drives, we'll load them onto S3, send them back to you, and it's surprising how high bandwidth FedEx can be if you're moving petabytes of data around. And we have Direct Connect, which allows you to set up a dedicated 1 gig or 10 gig E connection, as many as you need, between your hosting provider and the AWS cloud. And that's a dedicated connection that you can provision by the hour. We also have a number of partners that provide data integration capability, as well as systems integrators and boutique consulting firms that can help you design an overall data movement and flow strategy. From an analytic perspective, we have really designed Redshift to work with whatever tools that you're using today. And so we use JDBC and ODBC interfaces, Postgres drivers. You can see we have a range of partners here that have certified Redshift for use with their systems. They've done their testing and validated and built integrations onto Redshift. And we also have some partner updates for folks that are not on here that I'll talk about in just a second. And a lot of our partners are also available on the AWS Marketplace. So you've heard about this. This is essentially an app store for AWS software. It makes it really easy to launch applications and have them run on AWS and talk to your AWS resources. One of our partners on here, Jaspersoft, has done a ton of work in making it easy for their system to actually auto-discover your Redshift and RDS resources. So really simplifying even more the integration steps there. And also a couple of other updates from partners. Burst is available on the marketplace as well. And one of our newest partners, Sisense, has done a ton of work integrating Redshift into their overall system. We actually got permission to share that Merck is using their platform, which provides a really easy way to do high-performance analytics on pretty simple systems. They have an ElastiCube technology, which is pretty interesting. And I'll have some, you can talk to Bruno, who's here in the back, if you're curious about that. And now I'll turn it over to Henry and Flo from Airbnb. Thanks, guys.
Good afternoon, everyone. And we're glad to share a little bit story about how we end up choosing Redshift at Airbnb. So let's take a look at our data infrastructure at Airbnb. Like any internet scale company, we have multiple data sources. We have data from key value store, DynamoDB, such, and also we do pixel checking to make sure our page are loading fast enough, and also we have our own logging services. All the web requests will end up sending requests to our own logging service, and all that thing, we are storing them in Amazon S3 right now. And traditionally, we use Hadoop family, including Peak, Hive, Castlog, and Cascading to process them, and then dump them into a relational database for a team of analysts to answer deeper questions. And so we like big data tools like Hadoop. It's really great at crunching terabyte and petabyte data, but they're not very interactive. And our old solution, as I just showed you guys, is like we use Hadoop to do nightly batches to process, and then we dump them into like RDS for interactive queries. And there are two problems. A, the size of our data is keep growing, and B, our team is growing as well. So the above solution will only work if those two doesn't exist. So as we grow, we need to look at other options to solve this issue. And we look at a few alternatives out there, but among all of them, I think the initial evaluation result from Redshift was the most promising. And the most of the work to adopt Redshift is among schema migration and also design your data processing ETL, and also make sure your current data will play really, really well within the limitation of Redshift. And we don't use it as a replacement for Hadoop, but rather as a complementary tool to Hadoop. And so we use it to mostly replace Hive queries. We have more than a couple of terabytes of data generated every day. And we have like a dozen of analysts. For the limitations I mentioned before, they have constantly go back to Hive, and which is really, really, really slow and slow down their productivity a lot. And so we did migration to Redshift at the beginning of this year. We have lots of JSON data, like many other web companies out there. So the first step is you need to figure out a way to transform those into a TSV or CSV format. And also, the other thing you need to deal with is right now, there's only 11 primitive types supported by this system. So you probably need to figure out a way to work around the limitation and load your data into Redshift. And as Rahul mentioned before, the distribution key and the sort key is very, very important when you design your schema, because that will affect how your data is distributed and when you run your join. And the performance will be improved a lot if you choose the right ones. So a few limitations here is, like string split is not supported. Also, percentile or regex are not supported as of now. And the other thing we found is like it would be nice if materialized views will be supported, because we tend to run big joins again. How we're doing this, we load the data. All the data is in S3 already, and also or DynamoDB. So it's really, really easy. It's basically just one command. The only thing we did there is to figure out each one of the data sets, what are the characteristics, and also what are the null values and specialties around the table. So you need to pay attention around that for a little bit. And then we did a little bit parallel loading. Originally, we were just using one process to load it, and we were loading more than like 1 terabyte data. It was taking a few hours. So we found like parallel loading helps a lot. And the other thing we ran into constantly was the Utf support. And the thing is, like, it supports up to 3 characters length of Utf characters. And for whatever reason, the data was noisy. So we had to do a little bit pre-processing there to strip them out. And the other thing you need to pay attention to is the null value handling. Right now, it can only actually specify one type of null value out there. As you can see, the other step will be how to wire Redshift into our existing ETL pipeline. And it's a problem that has been boggling us for a long time. And Flo, who is our team lead, built a tool to help us to wire everything together. You might have a bunch of Hadoop jobs. You might have some scripts to pre-processing them. And then we want to glue everything together to make it a whole pipeline. So without further ado, let me introduce Flo to talk about the tool called Kronos.
Thanks, Henry. Hi. So how many of you guys have actually worked on an ETL pipeline before? A fair number, right? So how many of you guys have used Kronos for, cron for that in the past? A couple, right? So that's how the state of the world was when I joined Airbnb. We used cron jobs and about 10,000 lines of bash in order to tie a number of jobs together. So Airbnb has a variety of data sources. We read data from databases such as MySQL. We read from, what other databases do we have? We read some from Postgres, some from some flat files. We get data out of Redis. And as Henry has mentioned, we use Hadoop in order to do some of the ETL work and join some of these data sets together and then repopulate some MySQL databases. So that was kind of the state of the art or state of the world when I joined Airbnb. And this is an example of a job flow at Airbnb. This computes the hosting viability, like basically how good is a hosting, and uses various data sources, various intermittent steps. There are a number of Hive jobs, a number of pig jobs. There are just some set and awk transformations. And the end result is basically data loaded into MySQL. Well, now it's actually been replaced. Data is now loaded into Redshift. But in order to tie all of these things together, we wrote a tool called Kronos. And Kronos is open source. You can download it from GitHub. If you go to github.com/Airbnb/Kronos, you'll find it. And the reason for writing Kronos was that when you're in the cloud, you experience a lot more variance in your network requests. For example, in latency, you also see oftentimes APIs that don't work the first time. So if you imagine a multi-step pipeline like this one, you oftentimes run into the issue that one of the jobs breaks and you're stuck. Your jobs don't progress. The next day, the analysts come to work, and none of them can do actually the work. And so then I spent a ton of time debugging that. So I think up until November, I would come to work on Monday, Tuesday, Wednesday, and spend the first 2 to 4 hours debugging this pipeline. And we have many more pipelines like it. And basically, that involved going into the log files, trying to figure out which step actually broke, and then rerunning those steps manually. So, and that was the motivation to build this tool, Kronos. And what Kronos basically does is it's a tool that's written on top of a cluster kernel. And the cluster kernel is called Mesos. And Kronos looks like this. This is the UI for Kronos. So what it lets you do is it lets you define job dependencies, and you can create jobs that are time-based or jobs that are dependencies of other jobs. And you can basically add repeats, so it can repeat daily, it can repeat hourly, just like you're used to it from Cron, but it lets you do much more than that. Kronos is a fault-tolerant, highly available system. It has many masters and many workers. And it's written in Scala. And as I said, it's written on top of this cluster kernel, which is called Mesos. Really, really interesting project. And what that allowed us to do, writing it on the top of Mesos, is we didn't have to write a single line of network code. And that's really big, I think, because, as I said, it runs on hundreds of nodes. I mean, we tested it on EC2 on hundreds of nodes, and it works very well there. But yet, no single line of network code. So there's no socket open in Kronos. The Mesos abstraction is a resource offer, and the workers all give you resource offers, or they give Kronos a resource offer, and then Kronos can say, hey, I have a job to run, and it runs it on one of the workers. We also built retries into Kronos, so you can actually say, you see that here on the right-hand side, you see with these 2 sample jobs that there are 2 retries. So if one of the APIs is down, it will be retried. Also, if one of the slaves goes away, and you start another one, it will automatically fail over. If you have 2 slaves running and one of them goes away, the other one will take over automatically. So that's all handled by Kronos. And this is an example for a job that has dependencies. Like the job that you saw earlier is also in there, but we didn't depict that because it looks a little messy. But the nice thing about this, for example, is that you see right away whether or not a job succeeded or it failed, because it will be either red or it will be green if it succeeded. And so when we pushed Kronos into production, I basically had no longer any work to do. So I came to work and was like, wow, I can actually start writing code again. So that was really good for us. Yeah, if you guys are interested, just check it out on GitHub, and more than happy to answer any questions. I think that's it, right?
Happy to take questions for really any of us. Did you want to talk about your performance results?
Sure, yeah. All right, cool. So, I'm on?
Go ahead.
Okay, cool. Here's the initial result we got when we first evaluated Redshift. So we were comparing Redshift cluster with 16 basic nodes to a EMR Hive cluster with 44 nodes. And the cost is listed there. And as you can see, the EMR cluster actually has a better node type than the Amazon Redshift here. Sorry? Yes, yeah. And then so we tried with a simple query, just do a group by over a little bit more than 1 terabyte of data. And here's the result. So Hive took 28 minutes, but in Redshift, less than 6 minutes. And this is really, really important to us because when the analysts write their queries, oftentimes it takes few iterations for them to get the right version. And as you can imagine, if it took the analyst 3 iterations to get the query right, it's going to take more than an hour versus in Redshift, it's like less than half an hour. And then we tried another complex query, which is a triple join, and with some group by right there. And the data set is slightly much smaller here. It's probably a half terabyte ish. And it worked really, really well. It's almost like 20 times faster in this case. So our conclusion for now is compared to the traditional databases we use, it's really, really responsive and can handle range queries and aggregations against really, really large data set very, very well. And it's very, very easy to adopt if you have people who has like some SQL background. And it's very cost effective, as Rahul mentioned before. But at the same time, you probably need to work with the limitations as of now. But if you can figure out a way to work around the issue, the benefit is huge. And that's all. Thank you, guys.
Thanks a lot, guys. Happy to take questions if we haven't. Go ahead.
Yes, I was just wondering, it's new to us. So I was just wondering, is Redshift pretty much a plumbing technology and infrastructure technology versus an analytics platform?
So Redshift is a data warehousing engine. So it's a system. It's a columnar SQL-based data warehouse. If you're running analytics, you can use a BI layer on top of it, or we have customers that use R or other packages. But really, it's designed to return queries on large data sets as quickly as possible.
Who is the prime direct competitor for this product on premises?
So the question is, who's the competitor? I mean, really at AWS, we're focused on our customers and letting customers choose the tool that's best for them. So, there are many relational data warehouses out there. They're all great systems. And customers will choose the ones that matter the most. I think what we focused on here is performance, price, and ease of use. Go ahead.
Do you have a pivot capability built into Redshift?
I actually don't know the specific answer to that, so I'd have to check our documentation. I mean, I think we support a fairly complete set of SQL and windowing functions. I think, as Henry mentioned, some things like regex and text functions aren't where they need to be, but that sort of feedback always helps us get better. But if we have it, it'll be documented, and if not and we need it, then I'd like to hear about it so we can figure out how to improve.
When you say that it's based on usage, is it based on the number of concurrent users we require from our system, or how do you calculate that when you say for usage?
So when we say usage-based pricing in the Redshift context, it's to do with the number of nodes that you have active. And active means dedicated to use. So if you run a 4-node cluster, from our perspective, you're using 4 nodes, and the size of those nodes will determine your hourly charges. It doesn't matter how much use you put on it or how much data you use or load or queries you run. It's really just hourly cost per node, size per node, and number of nodes. And if you have questions for the Airbnb team, feel free as well. They're happy to take them too. Sir in the blue jacket.
Any prospect for a query facility like MDX?
So the question is there any plans for supporting MDX? So we don't comment on our roadmap specifically, but we are always receptive to customer feedback, and that's how we make sure that we evolve in the right direction. So if that's a use case that can't be worked around other ways, that's good to know. And right behind. Yes, so in terms of looking at the evolution of the service, both we have a pretty active forum and where we'll post our announcements, as well as the AWS blog where any major feature releases will be covered. Oh, sorry, thank you. Go ahead.
Question for the Airbnb team. So you guys compared Hive with Redshift. Did you also look at writing your own MapReduce jobs? Or, I mean, I understand the whole thing around it being easy to use with SQL, but just from a performance standpoint, you also compare writing your own MapReduce jobs and comparing with Redshift?
No, we didn't benchmark our Hive jobs against raw MapReduce. I mean, that has been done. Other people have done that, and for most queries, that should be fairly negligible. So,
yeah, it wasn't really. We weren't looking to replace, traditional Hive jobs. More of like an interactive query. So that's why we benchmark against Hive.
Come back to you. Go ahead. So we let our customers make those kinds of decisions, and really because benchmarking in databases is so dependent on query and setup and data set size. From a technology perspective, Vertica is a columnar MPP scale-out system, and so is Redshift. So that's something that customers do, and we allow them to make the best choices. The hardware platform for Redshift is available on EC2. So that's something that a customer would do. Go ahead.
Yes, I was just wondering, like, just like you mentioned, Vertica, like suppose whoever Vertica guys can make their database of whatever the solutions available on EC2 as a compute engine. I, as a customer, suppose I don't have pricing issue with me at all. Would the performance of both be the same? And I'm just trying to understand what is the clear workload or use case scenario which really ideally suits your platform. How is it different than Vertica being delivered out of EC2 compute engine?
So, I think as I mentioned in the prior question, Vertica is also a relational columnar system, so I would expect workload characteristics to be similar. So it's really up to you from a perspective of the price, performance, and manageability dimensions on which you want to run. And so if you're running data warehouses on EC2, you'll be managing your own durability, you'll be managing your own hardware setup, your own node configurations. On Redshift, we'll manage that for you. So it really comes down to fit and appetite and where you want to spend your time and money.
Perfect.
Go ahead.
When it comes to Redshift, you said there's like you started at a single node, or you start scaling to multiple nodes, right? So when you look at a traditional data warehousing appliance kind of system, you have multiple nodes, and the data is like spread across the different nodes. So you have an MPP capability there. So how does Redshift ensure that when you start with a smaller number of nodes, you get the same amount of performance scale within an MPP?
Yep. So the question is, how does Redshift deal with data distribution across multiple nodes when you resize? And so Redshift is an MPP system, so we actually do physically redistribute your data when you add more nodes to the system, and that's what's happening in the background when we're parallel copying data to the new cluster. So we'll, pay attention to the table schemas and then distribute data as appropriate. So you'll end up with less data on each node in your larger cluster. You can also resize down if that makes sense for you at the time. But essentially, we'll pick the optimal distribution based on your schema for the number of nodes that you've selected in your target. Go ahead, sir. So we manage all of that for you. So there's no direct way for a customer to access that. I'm sorry, I didn't hear that. So the question is, where are the BI tools hosted? So really, that's a function of your infrastructure and the setup you want. We have customers that run BI on-prem and connect over the internet to Redshift. We also have customers that run their BI tools within the AWS cloud. It's really just choice.
So would that be then a simple ODBC, JDBC?
Yes, so it's ODBC, JDBC, Postgres drivers. We have the partners that I listed have done work to essentially certify and customize where appropriate so that they're generating optimal SQL for the characteristics of the Redshift system. But really anything you use that speaks JDBC, ODBC can talk. Maybe we'll talk after because I think I want to let a few other people. Just behind you, and then I'll come back.
The cost structure I gave, that was just for owning the database, right? Are there any overheads? Are there any costs for movement of data?
So for Redshift, we try to keep it very simple. So it's really, the cost is driven by the node size and the number of nodes. We don't charge for data transfer into Redshift or out of Redshift. If you're loading data into S3, any S3-related costs for your initial load will be charged by S3. We don't charge for backup storage up to the amount of active data warehouse storage. So that means that if you have a 4 terabyte cluster, you'll get 4 terabytes of free backup storage associated with that running Redshift cluster. So we've tried to keep it as simple as possible. There are some AWS-wide charges that apply in things like VPC, and those are all spelled out on our pricing pages. Go ahead, sir.
What's your advice on implementing data retention where you'd like to move granular data off after about a month, let's say?
Yep.
Is that something that would be a bunch of custom scripts, or is that something you're looking to implement into the...
So the question is how to deal with essentially time series tables and data aging. So we actually recommend that for customers that have a defined retention window to actually chunk their data, for example, keep a table per month, and then build a view on top of that that scans the entire working set. And that way you can, we have an unload capability, which is the opposite of copy. You can essentially drop a table onto S3 and archive that, and then load in new data as you go. So that capability is built in. It does take, it's not a setting that you define. The snapshots age out automatically, but anything within the data model you would control.
For the Airbnb team, how long did it take you in time before the transition to Redshift when you began to when you ended, and you could use it as an internal analysis tool?
I think it took us,
In case you didn't hear, the question was how long the transition time was, and was it a few weeks?
3 weeks.
3 weeks.
No.
I think we have time for probably one more. Go ahead.
You guys talked about a comparison between Hive and Redshift and Edge. Redshift has more Hive. So do you still use Hive and Hadoop?
So the question is, do we still use Hive and Hadoop now that we're on Redshift? The answer is yes, we still use Hive. We don't use it as much for interactive queries anymore. We still have some ETL, like it's not really ETL, but it's like some processing jobs that run on Hive. And that data itself is then loaded into Redshift. I think there was another question over there. The question is Kronos running on AWS? Yes, it is. Yes. So the question is, is it an example for taking your own application and embedding it with this system? Yes. So Kronos is a bash scheduler, so it can schedule any jobs. It schedules Redshift jobs via the Redshift API or command line tools.
All right, everybody, thank you very much. My email is up there. Happy to answer any questions one-on-one. Appreciate your time.